All right, day 11, Monkey in the Middle. As you finally start making your way upriver, you realize your pack is much lighter than you remember. Just then, one of the items from your pack goes flying overhead. Monkeys are playing keep away with your missing things. To keep to get your stuff back, you need to be able to predict where the monkeys will throw your items. After some careful observation, you realize the monkeys operate based on how worried you are about each item. You take some notes, which is your puzzle input, on the items each monkey currently has, how worried you are about those items, and how the monkey makes decisions based on your worry level. For example, then we can see we have monkey 0, which starts out with items 79 and 98. The operation it performs is takes the old value, multiplies by 19, and that's the new value. The test is whether it's divisible by 23, and if it is true, it throws to monkey 2, and if it's false, it throws to monkey 3. Same for the rest of the monkeys. They start out with sum. There's an operation. This one is addition. This one was multiplication. And this one down here is, well, it doesn't multiply by a number, but by itself. All right. Monkey 3 is just, yeah, okay. Each monkey has several attributes. Starting items list your worry level for each item the monkey is currently holding in the order they will be inspected. Operation shows how your worry level changes as the monkey inspects an item. An operation like new equals old times 5 means your worry level after the monkey inspected the item is 5 times whatever your worry level was before inspection. Test shows how the monkey uses your worry level to decide where to throw an item next. If it's true, if true, up here shows what happens with an item if the test was true, and if false, yeah, you can, you know, you. Yeah, and if false, it shows what happens with an item if the test was false. After each monkey inspects an item, but before it tests your worry level, your relief that the monkey's inspection didn't damage the item causes your worry level to be divided by 3 and rounded down to the nearest integer. The monkeys take turns inspecting and throwing items. On a single monkey's turn, it inspects and throws all of the items it is holding one at a time and in the order listed. Monkey 0 goes first, then monkey 1, and so on until each monkey has had one turn. The process of each monkey taking a single turn is called a round. When a monkey throws an item to another monkey, the item goes on the end of the recipient monkey's list. A monkey that starts a round with no items could end up inspecting and throwing many items by the time its turn comes around. If a monkey is holding no items at the start of its turn ends. In the above example, the first round proceeds as follows. So monkey 0 inspects an item with a worry level of 79. You see here, it starts out 79. And then probably going to multiply by 19. Yep, to get 1501. Monkey gets bored, worry level divided by 3. That gives us 500. That's not divisible by 23. So it throws it to monkey number 3. And so on and so on. So we have monkey 0 does all of its items, then monkey 1 does all of its items, etc. After round 1, the monkeys are holding items with these worry levels. Monkey 0 has 20, 23, 27, 26. Monkey 1 has 2080, 23, no, 25, 167, 207, 401, and 1046. Monkeys 2 and 3 aren't holding any items at the end of the round. They both inspected items during the round and threw them all before the round ended. This process continues for a few more rounds. After round 2, the monkeys are holding items with these worry levels. And you can see that, how it progresses over time. Chasing all of the monkeys at once is impossible. You're going to have to focus on the 2 most active monkeys if you want any hope of getting your stuff back. Count the number of times each monkey inspects items over 20 rounds. In this example, the 2 most active monkeys inspected items 101 and 105 times. The level of monkey business in this situation can be found by multiplying these together, which gives us 10,605. Figure out which monkeys to chase by counting how many items each inspects over 20 rounds. What is the level of monkey business after 20 rounds of stuff slinging simian shenanigans? All right. Yep, let's take a look. Okay. So, just this part right here really has to do with part B. So let's just ignore that for a second. As usual, we start with getting all the lines, and then we initialize all these variables. So we have operation, items, if true, if false, and monkeys. Monkeys is going to be the list of our monkeys. And these 4 variables here are the things that we learn about the monkey as we are parsing the input. And then once we reach an empty line, we know that we have all the information for the monkey, create the monkey, put it in the array, and we move on. Okay. So that's what happens here. Let's look at the sample text again. Okay. So if it starts with monkey, it doesn't matter. We just continue. If it starts with starting items, then we split by, excuse me, we skip over the first this many characters, and then we split by comma space, and that gives us the items, and then we turn them into integers instead of strings. We do kind of the same thing with divisible by and if true and if false. You know, that's pretty straightforward. Divisible by is, you know, if the line starts with space tests colon space, then we know it's this one, and then we grab the last word and turn that into an integer. We do the same thing here with if true and if false. Right, operation is one of the trickier ones. If you watch the replay, I had a lot of trouble with this one, because apparently I am not completely clear on like the order of evaluation here. So my original attempt looked something like something like this, right? And when we're parsing the first monkey, this would be no, that's the first one multiplies. So sorry, let's move this down here. Yeah, so that's what it looked like when I had done it. So I would create this lambda operation. So no, let's parse it first. So we grab the line. Don't need that anymore. That was for debugging. Sorry. Okay. So we know that we are looking at the line that reads operation, because that's what we have up here. Then we split by colon space, means that we get this right here as our final argument, our final element. So that's what we have as our op. And then I assert that it starts with new plus because I wasn't sure what I was going to see in the real input. And rather than getting tripped up by that, I just put in an assert so that it would error out if it looked unusual. Okay, whoops. Next up, we first split by equals. Yeah, because then we have this as our final argument or element, and then we split this by spaces, and that gives us old, which is always old, and then the operation and the second argument. Okay, and then if op is plus, and if argument 2 is old, then the lambda is pretty simple. It just takes an x and does x plus x. If it is not, if the second argument is not just the string old, then I would create this lambda that would yeah, perform this operation. It would take the x as the input and add the integer value of the second argument up here. Yeah, and it's exact same recipe down here for multiplication. The problem, as it turns out, is that this is all lazily evaluated. So every time I go through this loop, I find a new value for arg2, right? Because I'm parsing a new one. I'm parsing a new monkey, so the operation is going to have a different second argument. And this will evaluate based on the value at that time. So if arg2 has a different value once I actually end up performing this operation, that's the value that ends up applying, and that took me a long ass time to find out. So the solution I came up with was, pretty terrible. It's you can see it in Git or in the replay if you want. But this is a little trick I picked up from one of the other people doing it, doing these exercises. Wasn't exactly like this, but basically what happens here is that we are defining a lambda expression, and with a keyword argument called arg. It's a keyword argument because it because you provide the value as you define it, and this is evaluated at definition time. So when we define our lambda expression, this gets evaluated, and then it's passed in as that arg. So we have that here even when we finally execute it. So that's a really cool way to get around this problem of what are we looking at, when is it evaluated, and all this kind of stuff. So that takes care of that. That's one I removed before. Okay. And the last thing we do is when we find an empty line, we create a new monkey, and we pass in this bit of information that we parsed. And we add it to the list of monkeys, and we reset all these variables, and that's it. By the end of this, we have all of our monkeys. I added an extra line feed over here to make sure that this would happen for the last monkey too. Okay, and at this point we're just this. You can ignore this. This is for part B. Okay, so yeah, forget all about that. That's part B for now. Okay, so as usual, we define a function that modifies our state as though we have progressed one round. So we pass in monkeys, and then we perform these operations as per the instructions. So we go through the monkeys, and for each monkey we go through its items. We increment the number of inspections that it made, because that's what we actually want to, that's what our answer that we have to give is going to be based on. We pop an item off the list. Pop 0, we like the first element. He specifies that several times in the instructions that they do it in order. I can't see why that matters. But I did it anyway. So pop 0 pulls the first element from the list and stores it and assigns it to item. Then I perform the operation as given over here to the item. Then I divide by my worry decrease, which is 3 in part A. The double slash means that it's an integer division, so any remainder is just discarded. And then we have this part, which is only relevant for part B, so just ignore that for a second. And then we perform the test, and based on the outcome of that test, we append the item to In this case, it's either monkey 2 or monkey 3. And do that 10 times or 20? 20 times? Yeah, 20 times. Yeah, we can see it rounds is 20. Then we order it. We order the monkeys by number of inspections. We take the 2 highest ones, we multiply them, and boom, that gives us our answer. Okay, let's take a look at part B. Part 2, part B. Anyway, you're worried you might never ever get your items back. So worried, in fact, that your relief that a monkey's inspection didn't damage an item no longer causes your worry level to be divided by 3. Unfortunately, that relief was all that was keeping your worry levels from reaching ridiculous levels. You'll need to find another way to keep your worry levels manageable. I should have read this more closely. There was a good hint there. At this rate, you might be putting up with these monkeys for a very long time, possibly 10,000 rounds. With these new rules, you can still figure out the monkey business after 10,000 rounds. Using the example above, after round 1, these are the main blah, 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 blah. And after 10,000, these are some pretty high numbers. After 10,000 rounds, the 2 most active monkeys inspected items 52,166 and 52,013 times. Multiplying these together, the level of monkey business in this situation is now a very large number. Worry levels are no longer divided by 3 after each item is inspected. You'll need to find another way to keep your worry levels manageable. Starting again from the initial state in your puzzle input, what is the level of monkey business after 10,000 rounds? And the trick here is, the naive thing, which is obviously what I what I just did immediately and tried it. So again, part B is a generalization of part A, right? So you in part A you had to divide by 3. In this one you don't. Okay, so we make the factor by which your worry decreases, we make that a variable that you can pass in. And then in part B, that would be 1. So you divide by 1 and nothing changes. And you would pass in rounds equals 10,000. So that's what you do in part B. Okay, so what happens if you just do that? I guess we've removed the bits and pieces. Can we just try it? That was not supposed to work. Why did that work? Oh, I haven't saved it. There we go. This is supposed to get stuck. Yeah, there you go. See, it's just spinning there, and it's gonna. When I was doing it yesterday, I had it print out which round it was at. Whenever it started a new round, and up until 700 or 800, it was fast, and then all of us it just grinds to a halt. It took me forever to realize this, even though there were plenty of hints in the text. These numbers get real big real fast. We are talking hundreds and hundreds of digits very quickly. And that means that all these manipulations just take forever. So I needed a way to keep those numbers manageable without messing up the tests. So I needed to get the same result as though I had been working with the huge numbers, just without using the huge numbers. And yeah, this is still sitting there. And this is what I came up with. So basically what we're doing here, we're using a little bit of number theory. Okay, so all of these different operations, testing whether dividing something by a number and then what the remainder is, and whether it's, no, not what the remainder is, but whether it's divisible. All of this holds true even if you perform all your operations under a modulo I don't know how to say that. So all these operations, you can do them modulo a certain number, and you're still going to get the same results. I should probably explain that at some point, but for now, if we just the trick is to multiply all these numbers that things are supposed to be divisible by, and you can use that to use that as the modulo whenever you're doing the operations. And what that means is that the modulo is like any result you get from any operation, you divide it by the modulo, and you use the remainder from that that division. So it's like you cap your timeline, or not timeline. You cap your number line at that number, and whenever you get there, you wrap around and start over. And we can prove that that doesn't affect the results of this. So that's what I did. I took all the divisible by, multiplied them, passed them in as the modulo, set the modulo to a ridiculously large number by default, so that part A would still work. And yeah, so part B is just part A with 10,000 rounds and no worry decrease. And then this doesn't change anything even for the smaller numbers, so I just put this in, whether it's part A or part B, doesn't matter. Yeah, and as soon as I had that, it was pretty fast. Boom, and I had my answer. Yeah. So that this little trick here, I think, is something yeah, that was a really cool trick. I'll probably need that again at some point. So that's a good little one. Yeah. Other than that, it's not a lot to say here, I think. Yeah. So I guess that's it. If you have any questions or comments, just leave them below, or if not, just like and subscribe, and I will see you tomorrow.